Good afternoon, and thank you for joining us today as we host this special information session on ionoculation. My name is Beverly Chung, and I am the Director of Marketing and Communications at Well Resources. I will be the moderator for this session, and it is my pleasure to be joined by Ms. Belle McGregor, Product Analyst, who will be taking you through the content today. This presentation is intended for informational purposes and will be recorded and uploaded into the public domain for future reference. As society becomes increasingly carbon conscious, the reliance on clean fuels is becoming more and more pronounced. However, the traditional methods in which clean fuels and clean fuel additives are produced may pose serious health, safety, and environmental risks. The focus of today's discussion will be on alkylate and alkylate production and how a safe and sustainable alkylation technology licensed by Well Resources can eliminate the use of hazardous alkylation catalysts. At this point, please turn your attention to our disclaimer for this presentation. As the materials are intended for informational purposes only, it may not contain all of the information necessary for an in-depth analysis. However, for those of you in our audience who wish to learn more about our ionoculation technology, I strongly encourage you to visit our website at wellresources.ca or contact a member of our team at info@wellresources.ca. With that, I will now turn things over to Belle.
Thank you, Beverly, for that wonderful introduction. We'll start this presentation with a brief introduction to Well Resources. We are a Canadian clean tech company that is focused on green, clean, and safe technology development and process licensing for the petroleum sector. Our company's mission is what we call effective resource utilization, where we aim to provide our clients with innovative, adaptive, and disruptive process solutions that build a sustainable future. Over the years, we've established our market niche in focusing on what many would consider traditional refinery waste or byproduct streams, which encompasses both light off-gas streams and the so-called bottom of the barrel. Our view is that reducing waste and, where possible, turning waste into value-added streams will be beneficial for both the environment and society if this can be done in a responsible and sustainable manner. Well Resources currently offers two unique and commercially proven technologies to the downstream sector. One of these technologies, shown at the bottom, is the selective extraction of asphaltenes, or SELEX process, and this is a carbon granulation and removal process for upgrading and decarbonizing the bottom of the barrel. The other technology is our safe and sustainable alkylation process called ionoculation, which makes use of a proprietary composite ionic liquid catalyst, and this technology is the focus of today's discussion. The objective today is to provide you with an overview of the ionoculation technology and give you some insight into our numerous commercial successes within the last decade. We're going to start the discussion today with an overview of alkylation, seeking to answer the questions: what is alkylate? How is alkylate produced? And why are traditional alkylation processes inadequate? We'll then go on to describe the ionoculation process, including what makes it unique, what are the advantages, and what is the commercial status of the technology. Alkylation overview. The alkylate market is lucrative and has seen good historic growth. It is expected to grow even further over the next decade. In 2021, the global alkylate market was estimated at $1.15 billion, and it is expected to exceed $1.5 billion by 2029. This represents a compound annual growth rate of about 3.8% for that period. This growth is underpinned by a variety of factors. In the developing world, robust population growth and increasing standards of living are driving gains in overall gasoline consumption, and by extension, alkylate consumption. In developed economies, overall gasoline demand is expected to drop throughout the years of 2025 to 2050. But nonetheless, we see a shift towards higher performance fuels for higher efficiency engines, which supports the alkylate demand. From a process chemistry standpoint, alkylation is simply a chemical process where an alkyl group is attached to an organic substrate. But in a refinery setting, alkylation refers to a particular process that reacts light, mixed olefin feedstocks into predominantly C8 compounds for blending into the gasoline pool. Alkylate is known for its inherently high octane number, typically in the range of 92 to 96, and as high as 98 to 100. It increases the knock resistance of a fuel, is clean burning, is free from olefins and aromatics, and has low sulfur content. When we look at the various alkylation processes on the market, an important question to ask is, how do we get from point A to point B most effectively, contextualized by the technical, economic, and environmental factors? Traditional alkylation processes have been used for roughly 80 years, and they make use of strong acids to break chemical bonds and facilitate that alkylation reaction. The main catalysts currently in use include hydrogen fluoride or concentrated sulfuric acid. With these catalysts being strong and highly corrosive acids, the physical processing infrastructure is typically constructed using expensive and exotic metallurgy, and operators require the use of robust safety and containment systems. This is especially true for hydrogen fluoride, as it has a propensity to vaporize into a dense toxic cloud that can threaten the livelihoods of plant personnel and the public. With sulfuric acid, large volumes of catalyst are required, and this poses an environmental risk when considering the high emissions intensity associated with its regeneration. WELL's ionoclation technology leverages new sciences to address both the safety and environmental problems commonly associated with acid-based technologies without sacrificing performance or cost. And this is important because refinery infrastructure all around the world is aging. In North America, we see a trend of cost cutting through maintenance and capital deferment to get longer run lengths, and a general cautiousness towards newer process investments. And every couple of years, near-miss incidents like these not only threaten the livelihood of businesses, but also the safety of workers and the community at large. More frequently, old and unreliable refinery processing equipment may not necessarily lead to a near-miss incident, but unplanned shutdowns may lead to market disruptions and other business interruptions. Acid alkylation processes can be especially problematic as corrosion risk combined with aging infrastructure can form a recipe for disaster. On the left is an instance from 2019 where a U.S. refiner's HF alkylation unit suffered a catastrophic disaster, and the operator subsequently filed for bankruptcy protection. Earlier this year, another explosion in an alkylation unit in South Korea tragically claimed the life of one and injured 9 others. Nobody ever wishes for this to happen. Events like this have become topics of heated debate as to whether the use of toxic and dangerous chemicals in refineries should even be permitted, especially if these operations are close to urban centers. As stakeholders, including investors, governments, and the public at large, start demanding that companies focus on improving the environmental, social, and governance components of their operations, we expect refinery process safety will only become more heavily scrutinized. As more and more incidents like these occur, it becomes almost impossible for regulators to sit back. They will demand action. Case in point, United States Chemical Safety Board, October 11th, 2022. The Chemical Safety Board published its more than 100-page final report on the 2019 Philadelphia Energy Solutions fire and explosion, where they highlighted the inherently unsafe nature of HF and what went wrong during that operation. As part of its recommendations to the EPA, the Chemical Safety Board said that technologies are being developed that could be safer alternatives to HF alkylation, and refiners should periodically evaluate these available alkylation technologies. The CSB is recommending that EPA require petroleum refineries to conduct a safer technology and alternatives analysis as part of their process hazard analysis under EPA's RMP rule, and evaluate the practicability of any inherently safer technology. To put it this way, in North America, regulatory authorities are stopping just short of a call to action forcing the implementation of safer alkylation alternatives. But as new technologies become more widely adapted, it will be increasingly difficult for refiners to justify continuing the operation of these unsafe acid-based alkylation processes. In engineering and occupational health and safety, there's this principle called the hierarchy of hazard controls. At the top are the most effective ways to control your hazards, starting with outright elimination. As we move down this inverted pyramid, we observe a decrease in effectiveness while costs are additive with each layer. With traditional alkylation processes, the hazard is the catalyst itself. Being reliant on acid catalysts to run a process, refiners are then left with engineering, administrative, and physical protective controls to mitigate that risk. For an HF alkylation unit, for example, this will include safety measures such as water cannons, water curtains, secondary containment, advanced air quality monitoring systems, specialized additives, containment suits, and specialized training and evacuation procedures. With our ionization process, the intent is to outright eliminate that hazardous catalyst, enabling a refiner to simplify their operations, lower their costs, reduce the risks, and in some cases, save lives. Regardless of the safety measures put into place, there are other real costs associated with the use of inherently unsafe processes in refining operations, which will affect a company's bottom line. Here is a sample from a Reuters article from January 2020 discussing the rising cost of insurance for refiners. In some cases, insurance rates have increased by 25 to 100%, and some refiners have subsequently reduced their coverage as a result. This means that in the unfortunate event of a failure, the financial implications could be much greater. We'll now move on to the discussion of the ionization process itself, which derives its name from the composite ionic liquid catalyzed alkylation. Ionization is a commercially proven process backed by over 20 years of research and development in the ionic liquid space. The process is characterized by 5 sub-processes: feed pretreatment, reaction, product separation, product treatment, and catalyst regeneration. The first step in any alkylation process is to pre-treat the feed so that it becomes compatible with the reaction system. Here we will be looking to remove key contaminants such as sulfur, water, and oxygenates. Once treated, the feed is sent to the reactor, where it makes contact with a dense circulating catalyst that facilitates the alkylation reaction. Afterwards, a series of settlers and separators are used to differentiate the reaction products, unconverted reagents, and catalyst, recycling as needed. The alkylate product may be further subjected to a product treatment method depending on the end user's requirements. At the bottom of this flow diagram, an extraction process is used to remove a small quantity of spent catalyst from the system in the form of a benign solid, while the vast majority of recovered catalyst is routed to the catalyst regeneration unit. At the catalyst regeneration unit, Makeup active reagents are introduced to offset the spent catalyst removals. Regenerated catalyst is then routed back to the reactor, and an organic chloride compound is injected to supplement the catalyst activity. Here, the key process highlights for ionic chelation are summarized, which we will cover in more detail. They include the inherently safe catalyst, enhanced performance measures, a non-corrosive system, and the integrated catalyst regeneration. The key to the ionic chelation process is our proprietary composite ionic liquid, or CIL catalyst, which is a specially formulated, non-volatile liquid salt material. This replaces traditional acid catalysts, increasing the safety for refinery personnel and the public. Broadly speaking, the use of ionic liquids are based on relatively newer material sciences and innovations. Ionic liquids tend to have melting points below 100 degrees Celsius, and many parameters are available for fine-tuning their characteristics and applications. The chemical composition will affect key properties such as melting point, viscosity, density, solubility, and reactivity. And while acidity of ionic liquids can also be manipulated simply by controlling the concentration of certain species, many still tend to be corrosive. If you now move to the next layer of complexity in ionic liquids, material sciences, and introduce additional metallic species in the formulation, you get what is known as a composite ionic liquid, where the chemical, physical, and reactive properties can be manipulated even further. Some notable characteristics about the ionic chelation catalyst is that it is both non-corrosive and exhibits zero or near zero vapor pressure. This means that in a spill scenario, the catalyst remains as a liquid, which enables safe and easy containment. Plant operators working in the vicinity of an ionic chelation unit do not require any special PPE beyond what is customarily deployed in refining operations where personnel may be exposed to light hydrocarbons. Our proprietary catalyst uses a conventional chloroaluminate ionic liquid platform, modified with a transition metal to enhance the reaction mechanics. This enables the catalyst to overcome poor product selectivity issues that are commonly associated with simple ionic liquids, without the need for acidic additives such as hydrochloric acid. Here, it should be noted that when we refer to the term chloroaluminate ionic liquid, this means any ionic liquid that contains the tetrachloroaluminate anion. The CIL catalyst is fine-tuned to have high selectivity towards producing the most valuable high-octane gasoline constituents, while minimizing the production of undesirable byproducts such as acid-soluble oil. As you can see on the table, simple ionic liquid is not capable of achieving a selective reaction, unlike its composite counterpart. The facilitated alkylation is very much stoichiometric, and we can reasonably predict the performance of the process based on feedstock analysis. N-paraffins are non-reactive in our process, and we recommend excess isobutane in the feed to ensure complete conversion of the olefins. C4 olefins will be alkylated with isobutane up to C8. C5 olefins will be alkylated up to C9, and so on. The CIL catalyst was developed over many years, spanning numerous iterations and formulations. The red iterations in this diagram represent the first trial stages in the late 1990s, where the starting point was a simple chloroaluminate ionic liquid platform, and where the research team sought to modify the product yield and selectivity to acceptable tolerances. It was found that this could be achieved by modifying the aluminum chloride mole fraction and also doping the ionic liquid with acidic additives such as hydrochloric acid. Unfortunately, these systems were still corrosive, and the logic was that if corrosion still persisted, Any new technology based on ionic liquids would not represent a stepwise change from the existing acid-based systems. Next, in the yellow, are what we call the second trial stages, where the aim was to remove that corrosion factor while preserving the performance of the catalyst. In these trials, those goals were achieved, but it was found that the formulations tended to produce suspensions with the alkylate, which made it difficult to separate in commercial operations, therefore making it non-viable. Lastly, with a little bit of luck, the research team was able to finally develop an optimal CIL catalyst that could overcome all of the issues mentioned previously, in that it produced the desired alkylate, was non-corrosive, and could be easily separated from alkylate product. Due to the non-corrosive nature of the catalyst, all of the ionization process equipment is manufactured with low-cost carbon steel. The process is also run under mild operating conditions, which lower both the capital and operating costs in relation to the reference technologies. The materials of construction will undoubtedly have a significant impact on project budgeting. But beyond that, in today's day and age where supply chains are in disarray, the sourcing of readily available carbon steel equipment as opposed to specialty equipment can also benefit the project execution timeline. The images on this slide showcase key pieces of process equipment from an ionization unit constructed in 2013. This unit operated continuously for 3 years until it was temporarily shut down for a government-mandated safety inspection. The inspection was quite rigorous. There were no signs of corrosion within the equipment, no mechanical or maintenance issues needed, no safety incidents, and no problem shutting down or restarting the unit. Ionization includes a mild on-site catalyst regeneration unit, which significantly reduces emissions as compared to energy-intensive acid treatment processes. When using sulfuric acid, for example, the regeneration process entails a thermal decomposition near 1,000 degrees Celsius into gaseous sulfur dioxide, water, and oxygen. This gas mixture is then scrubbed clean, cooled, condensed, and reformed into acid. In our process, a relatively small amount of spent catalyst is ongoingly removed as a chemically benign material. You could consider ionization a self-cleaning process, since ongoing ejection of this material prevents any clogging or plugging issues. Here, you can see the various stages of byproduct handling, moving from a benign paste discharged from the process, all the way to a dry mineral-like solid. This material is accumulated and removed every few days up to 2 weeks, depending on the operator's needs or preference. Existing users of the technology have been approved to dispose of the material by landfill. The spent catalyst removals are offset with what we call catalyst active reagents, which are lower cost raw materials that reconstitute into CIL catalyst at the regeneration unit. From our experience, our clients' decisions to opt for a self-cleaning process with a nominal makeup requirement versus an option to completely regenerate catalyst all comes down to a matter of cost and emissions. As mentioned earlier, ionization is technology that has been decades in the making. Catalyst and early process development commenced in 1998, and the first lab-scale pilot was developed in 2003, capable of processing 20 metric tons per year. In 2005, our research group was invited to conduct a commercial catalyst retrofit test for a 65,000 tons per year sulfuric acid alkylation unit at a PetroChina refinery. This test yielded some promising results, and it also allowed the team to gather important information to improve the design for future iterations. Notably, the retrofit increased the process unit's capacity by 40%, while increasing the light alkylate yield by 5%, and the overall alkylate yield by 2.3%. The alkylate research octane number was also increased by 3.8 points to 98.8. Over the last 5 years, ionoclation has become the alkylation technology of choice amongst refiners looking to modernize their operations and improve their safety profile. The first commercial unit was commissioned in 2013 by the Chinese independent operator, Dayan Chemical Company. This was a 100,000 tons per year greenfield and standalone alkylation operation that purchased feedstocks from the local market and sold the alkylate back into that market as a value-added product. In 2018, PetroChina commissioned its first ionoclation unit at its Harbin refinery with a processing capacity of 150,000 tons per year. The operator has disclosed that the total turnkey capital cost for the project was a mere $46 million. The next year, PetroChina followed up this unit with another one size 50,000 tons per year at its Golmud refinery. And that same year, Sinopec commissioned its first of 3 units, each sized at 300,000 tons per year. Here is the unit at the Zhujiang refinery. As reported by the operator, the total turnkey cost of this project was $78 million US. The second Sinopec unit was at its Wuhan refinery in 2020. This unit set a milestone as the world's first commercial revamp from an existing HF alkylation unit using ionic liquids. This revamped unit was one of 2 remaining HF alkylation processes in operation in China. The Sinopec Anqing unit's construction was completed in 2020, but due to the coronavirus pandemic, the commissioning was put on hold until Q1 earlier this year. Lastly, PetroChina constructed another 150,000 tons per year unit at its Dagang refinery, and this unit was commissioned in August 2022. In total, ionoclation has been commercially proven for almost a decade across 7 units with a total alkylation capacity of just over 33,000 barrels per day. Plant data from the Dayan, Harbin, and Zhujiang refineries have been published in 2018, 2020, and 2022, respectively. Lastly, I want to briefly discuss options for converting existing acid-based alkylation processes to ionoclation. Regardless of which process you are converting from, the minimum equipment required will include the ionoclation reactor and catalyst regeneration system, as they're unique to our process. In addition, depending on the mechanical integrity of the existing equipment, a new product fractionator may or may not be required. For revamping a sulfuric acid system, much of the existing cooling system may be reused. But for revamping an HF alkylation system, which typically doesn't have additional cooling, refrigeration might only be a consideration if an end user intends to produce even higher quality alkylate. But by all means, the inclusion of a dedicated cooling system is not required. In any case, each conversion scenario is considered on a case-by-case basis, and the goal is to reuse as much of the existing infrastructure as possible, having minimal impact on operations while occupying the least amount of space. To summarize, ionoclation is a safe, sustainable, and viable alkylation technology that provides an alternative to the traditional acid-based processes. We make use of a non-corrosive composite ionic liquid catalyst that facilitates the production of high-quality products, and all of the process equipment is manufactured using low-cost materials. This is also a commercially proven process where the scale-up considerations have been de-risked. In total, 7 units have been commissioned, including 1 for the elimination of HF, and nearly 1 decade of operational demonstration has been generated. I'll now turn things back over to Beverly for some final remarks.
Thank you, Belle, for that insightful presentation. Well Resources strongly believes that there will be a place for safe and sustainable clean fuel production in the energy mix of the future. However, in light of recent incidents that have highlighted the inherent dangers of acid-based alkylation processes, the refining industry is now facing increased pressure to look for safer alternatives. Ionicylation has the potential to transform the landscape by providing refiners with a commercially proven alternative that doesn't have to break the bank. Our company remains committed to providing the industry with leading-edge and common-sense solutions to build a sustainable future. On behalf of Well Resources, we would like to thank all of our audience members for joining us in this presentation today. To learn more about our full range of service and technology offerings, please visit our website at wellresources.ca. If you have any questions or comments on the subject matter presented today, please feel free to reach out to one of our experts at info@wellresources.ca. Thank you.